Assalamualaikum warahmatullahi taala wabarakatuh, and very good morning to all panel and listener at the conference. So today I'm going to present about my conference paper, which has the title of Development of Onboard Chart Weighing System based on linear strain from chart structure. So my name is Muhammad Fahmin bin Razaki, and this study is supervised by Dr. Ng Kok Moon. Okay, first, so let's start with the abstract part. So for the abstract part, first is we're going to touch about the objective, which is we want to develop a prototype of OBWS, which is on-board weight system using linear strain from the chart structure. And then the method we use to develop this prototype is we install the strain gauge on the truss I-beam, which is the connection and with the connection of the full bridge piston circuit. And then we do the testing for the linearity behavior. And then we analyze the result. After we analyze the result for the linearity, we do system implementation, which is the embedded system using ESP and also ADS 115 ADC, and also some programming that involve micro Python program. Next, we will move on to the introduction part. So, as in the transportation system, truck is very essential for goods transport, but currently nowadays in our country, for example, overloading threaten road safety and accelerate infrastructure damage. So, and there are studies that shows that overloaded truck make up over 60% of vehicle and 21.5% in Malaysia, which is a lot amount of percentage there. So, in another case, in another case, which is the current system that we have nowadays, which is the conventional weighing methods such as weight station and weight in motion are either time consuming or lack continuous monitoring. So for the OBWF, which is for our study using the strain gauge, we will present a promising solution for accurate real-time monitoring while we still supporting the safety, compliant, and smart city initiative. So for this particular study, we have two main problem statement, which is the first problem statement is the mechanical stress response on the truck component like the I-beam must be linear for accurate weight measurement. So and the strain weight relationship for this component remains uncertain and under investigated. So we want to investigate the certain truck component uh, that give the linear response to develop our onboard weighing system. And then the next problem statement, which is problem statement 2, is about the conventional truck system, such as the weigh station and embedded load cell, which is the current system that we have nowadays, are limited by installation complexity, lack of real-time monitoring, and downtime that make them unsuitable for continuous onboard weight tracking during the operation of the truck. So based on the problem statement before, we come up with the two objectives aligned with the problem statement 1 and 2, which is the first objective that we come up with. We want to investigate the correlation between the mechanical strength, which is the signal output and measure with strain gauge and weight applied to the truck's I-beam. And the next objective is we want to develop an OBWS prototype for measuring weight on a truck loading bay. Okay, so for the first step for the methodology is to identify the optimal strain gauge placement on the truck structure. But before that, I want to explain about the strain gauge sensor, which is strain gauge is sensor that used to measure strain, which is the deformation or change in the shape of material when subjected to the force, pressure, or weight. So the strain gauge that we will use is a model of BFBA 300 TAA with a resistance of 350. So to maximize the usage of the strain gauge, uh, the the placement of the strain gauge need to be identified because it's very crucial for reliable deformation measurement. So we identify the location of the strain gauge placement on the structure, which is on the I-beam. So we choose this particular component because as one of our literature review from Lepanen, which is he conducted the FEA on the truck trailer's frame and identified the additional stress peak area that at the connection plate of the first few transverse pin. So this we took this concept from the this particular literature and decide to do the uh, at- the strain gauge placement at the I-beam. So next we will move on to the next part of our methodology, which is the experimental setup for strain measurement on I-beam using full bridge. So first step is the strain gauge installation. So we install the strain gauge on the I-beam and then connect it to the full bridge Wheatstone configuration, which is we want to improve the sensitivity and reduce noise, such as figure here. You can see the connection of the full bridge circuit. Okay, so we attach two strain gauge, which is one on the top of the beam, and then second is the bottom of the beam for each side of the I-beam. So we have two I-beam. So in total, we have four strain gauge attached on the I-beam, which is one of the structure. So however, before we do the installation, we done the surface preparation as the compulsory method before installation the strain gauge. So the strain gauge were connected as a full bridge configuration as I mentioned before, and then we connected the Wheatstone bridge to the weight transmitter as the signal conditioning circuit, and then we connect it to the multimeter so that we can read the voltage output from the weight transmission before. Okay, then the static loading experiment was performed, which is we want to access the strain behavior of the strain gauge that we installed earlier. So the water was used as the variable load medium as we fill the plastic water barrel with water with the increment of 25 kg until 325 kg. So uh, it has some increment there until 325 kg. So to examine the effect of load position on strain response, the barrel were placed at four different predefined locations, which is on truck loading bay. As you can see in the figure here, the truck has a location 1, 2, 3, and 4. As we divided the loading area into four quadrants, which is allow the evaluation of how different loading position affect the linearity of the strain gauge reading. So after we analyze the experiment data regarding the strain linear behavior of the strain gauge, next we want to develop the embedded system for the data acquisition and the display for the system. Okay, so the system is included an ESP32 microcontroller and ADSS1115 16-bit ADC and also the LCD for real-time output display. So the connection is the same as the experimental before, but with add-on of the some microcontroller and also the ADC. And as you can see here, one of the figures show that the output of the experiment has been shown in kg and also in ADC. And as you can see here, this is the flowchart of the embedded system algorithm that we use for the microcontroller, and also we this is the programming of the moving average algorithm that we use for this embedded system. So next we will move to the result and discussion part. So this is the experimental result and regression analysis, and the voltage result for different weights and location are shown in table 1 with regression statistics show in table 2, and also the graph in the figure that I show here is the voltage versus weight for all the location 1 until 4, which is referred to the table 1. So from our linear regression analysis and statistic for the location 1 shows a very strong correlation between weight and voltage, which is the R square of 0.9923, and with also with high precision sensitivity about 0.001 voltage per kg. For the location 2 is the best performance overall, which is the highest linearity of R squared 0.9982, lowest error and sensitivity of 0.0009 voltage per kg. Location 3 also give a very linear R squared value, which is 0.9959. And also the location 4 shows the lower correlation, but still a good linear correlation, which is R squared of 0.9716. It's still acceptable for this particular measurement. So overall, the I-beam shows uniform strain near the support, which is the structure that we choose, making it a good spot for strain gauge placement in weight sensing. Okay, next we will discuss about the performance of the embedded system for the data acquisition and display, which is involve the micro Python program. So for the result for this particular part, we have the very low percentage error, especially at the 100 kg and also 135 kg testing, which is 1% and 0.8% respectively. So the R squared value of the between the measured and the actual value is very high, which is 0.997, which is confirming the excellent linear fit measurement between the measured and the actual values. And also the overall average error is very low, which is 3.03%, which is within the acceptable range. And that conclude that this performance of the embedded system is very good.